Shrest, can you hear me? I'm not audible. I'm not audible. Give me a minute. This is working. Am I audible now? Shrest, am I audible now? Wait. I just, what I'll do is, see, I'm just checking. I'm checking all the possible alternatives. Can you hear me now? Huh? Now I'm audible? Okay, that's what. What happens is now, this will help me. Chalo, we'll start in a minute. Okay. Pavishi, you can hear me now? Yeah. Okay, great, beta, great. That's it. We'll start in a minute. I'll close the chat box. Okay. I don't know why Priya has not come yet. We'll wait 2 minutes. Okay, this is where we stopped last time, oxidation state. Now we are starting today with chemical properties. I had told you that I am not here in Bombay on Wednesday and Friday. The next lecture will be on Sunday only. Okay. I am going to Kota for some work. The coming Sunday, Monday, we will finish off halogen. Then I think by the next week, I'm finishing off P block elements. So now we are talking about what? We are talking about chemical properties. When we are talking about chemical properties, so we have to explain first of all, first statement that we say is halogens are very highly reactive elements. We say halogens are reactive elements. They are very reactive. So this itself is a give scientific reason why halogens are highly reactive. So we have to answer that. Now see, what is the basic of any chemical reaction? That's where the story starts. In any chemical reaction, reactant bonds are broken. And then they form atoms, ion, radical, whatever, and then the product bond is formed. So the essential is that the halogen, which is a reactant, its bond has to break. And if suppose the bond dissociation energy is very less, automatically what I mean, it breaks and forms atoms, ions, radicals, and then combines. Whatever has to happen will happen. Is this point clear? So that's the first answer. Why are they reactive? The first answer is the low. So halogens are reactive elements. Why? The answer. So this we can write it as a GSR, give scientific reason. Okay, or this can come as simply a statement as a distractor. Halogens are reactive because, whatever they can say, ionization, enthalpy, this, that. But the main point which we have to understand is, first and foremost, is that it has a very low bond dissociation energy. It has a very low bond dissociation energy. Very low bond dissociation. So if the bonds are weak, automatically it is understood that it is easy to break the bond. It's easy to break the bond and reactivity increases. So this is the very important point. Okay, low bond dissociation energy. Then the second, of course, there is another reason also, is the high electron gain enthalpy. They have a very high electron gain enthalpy. See, it's very simple. More energy is released by the halogen. The potential energy, because basically here what is happening, the potential energy of the atom, which is now becoming the ion, is high, because, and when it decreases by giving out the energy, so the anion will have a potential energy less than that of the corresponding atom. So the high electron gain enthalpy which it releases, is clear, makes the anion more stable than the atom. So that is why it is reactive. It gains electron. So high electron gain enthalpy. These are the two reasons. How does high electron gain enthalpy react? I told you. Is this point clear? The second very important this thing is very, very important over here. You see, this is a question which had, how did they ask that statement as a question in what you call entrance exam? Okay, it is the oxidizing nature. It is the oxidizing nature. So what are we realizing? We are realizing that halogens are, see, two statements. A statement, halogen are strong oxidizing agent. They are strong oxidizing agent. That is the first point. B, what happens? B. Fluorine is the strongest oxidizing agent. Halogens are strong oxidizing agent. First write the reason, then we'll come to the last point. Why? Because again, first reason is high electronegativity. So this is a give scientific reason why halogens are strong oxidizing agent. Okay, high electronegativity. High electronegativity, high electron gain enthalpy, and high ionization enthalpy. That you can add, but then generally these two reasons are the real correct reason. But then we have one more very important point in this oxidizing property, B. That is, fluorine is the strongest oxidizing agent. Fluorine is the strongest oxidizing agent. Oxidizing agent. Now, what is so important about this statement? See, if we try to understand how to get the other halogen, suppose I want from sodium chloride or HCl, I want chlorine. I have a very simple technique. The laboratory method of preparation of HCl is what? HCl plus acidified, HCl plus KMnO4, heat, you will get chlorine. We are interested in the other part, we are not this thing, chlorine. So what is the role of KMnO4 over here? KMnO4 is acting as an oxidizing agent. So chlorine, bromine, iodine can be what you call obtained by using an oxidizing agent, by oxidizing its halides, haloacids, so on and so forth. Is this point clear? But there is no, this is a very important point. There is no oxidizing agent available which can oxidize fluorine from its compounds. Fluorine from its compound. That was the reason why it took 50 years to obtain fluorine in the free state. I told you last time also, Henry Moissan, he obtained by electrolysis of what you call cryolite or something, not cryolite, Na3LF, yeah, I think it was cryolite and so now what did they do, They gave three distractors. Look, they said which reaction, how did they pose a question in the entrance exam? So you have HCl plus KMNO4. JE, it was a neat question if I remember. See, neat how the question is asked. HCl plus KMNO4 forms Cl2 plus all that. HBr plus let us say K2Cr2O7 will give you what? Br2. Okay. Then you have HI plus what do you call? You can even have straight away chlorine. It will give what you call I2. And then they had given this one. CaF2 plus H2SO4 forms F2. Which reaction is not possible? Which reaction is not possible? This is not possible. You cannot oxidize fluorine from any of its compounds. You cannot oxidize fluorine from any of its compounds. Are you understanding? So there is no oxidizing agent. Whatever we have learned, what are the oxidizing agents we learned? Sulfuric acid. Just a minute. Huh? I'm just keeping it. If this distortion comes frequently, then we'll change this thing. So what I was telling was, listen carefully, that there is no oxidizing agent available which will oxidize fluorine from its compound. You can't have HF plus what do you call some other oxidizing agent to give you fluorine. Like we had over here, HCl plus KMNO4, you got chlorine. HF plus say KMNO4, no such reaction is possible. So I'll just change this thing. It's giving a little. Give me a minute, just hold on. Hello, 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 hello. Priya, can you hear me now?
Yes, sir.
Okay, that's it. We'll continue. There's some problem, no? Live streaming has its own problem. Okay. So that's what I was saying. So very important point over here is such a reaction is not possible. I not should say yes. Such a reaction is not possible. So a statement that is the strongest oxidizing agent and there is no other oxidizing agent available which can oxidize fluorine from its compounds. That's the statement. And this is how they put it in the equation and this is how the question is framed. Is this point clear? Then we come to what. So I'll just give you a minute, please take it down and then we'll go to the other reactions. These are the two very important ones. Hello. So, we are having we are having some software issues since morning today. We'll have to do the complete formatting, but today we complete. 1 week I'm going on. I'll come back and fix this problem. So okay, I have some important. Have you finished this, Priya? Have you finished writing down this? Yeah. So I can continue. Then we have what we call as reaction with metals. There is an interesting question over here which they can ask. Okay. With not which they can ask, they have asked. I am discussing questions which they have asked only. A lot of questions, there is a theory part and that is converted into a question over here. So next is what? See, there is a theory and how is the question framed. So I'll give you both the aspect. Reaction with metal and non-metal. Basically, we'll talk about reaction with metals. Reaction with metals. So first of all, reactivity decreases. Reactivity decreases in the order of what? Fluorine greater than chlorine greater than bromine greater than iodine. So iodine will be least reactive with metals. That is okay. But the ionic character of metal halide bond, this is very important. The ionic character of metal halide bond is metal fluoride is more ionic than metal chloride, more ionic than metal bromide greater than metal iodide. Now this is a straight question they can ask. But what question they had asked, I will tell you from a previous year question paper. You have aluminium fluoride, aluminium chloride, aluminium bromide, aluminium iodide. And the question they had asked was, which is soluble in water? Which is soluble in water? See, look at the theory. The theory says that metal fluoride will be most ionic. Automatically here what happens? Aluminium fluoride is more soluble and these are covalent. This is most ionic. In fact, this is ionic. It's clear? And this is covalent. So here was a statement and here is the question which is framed. That is aluminium fluoride is soluble in water. It's clear? So then, one more thing we should know while we are talking with this about this is, I'll just write down the statement as it is because I don't want to write it in my own language. That can be little. Halides of metals. Halides of metals having low ionization enthalpy. Having low ionization enthalpy. Okay, which are they? Sodium, magnesium, lithium. Lithium is sodium, potassium, rubidium, cesium, francium. That alkali metal and alkaline earth metal. That's it. They are ionic. They are ionic in nature. Is this quite clear? Whereas metals having high ionization enthalpy are what do you call covalent in nature. See, let us look at it like this way. We have lithium, sodium, lithium fluoride. We could even have beryllium. Remember beryllium fluoride. We had discussed beryllium fluoride as a covalent compound, sp hybridization. beryllium chloride, because beryllium has a very high ionization enthalpy. Example of this is we have beryllium BeCl2. Beryllium is a metal, but beryllium chloride is ionic in nature. Bf2, we discussed it as a sp hybridization. So this is the reason. Ion enthalpy is more. It does form a compound covalent in nature. This is clear. Then, now, if they show that the second point is in this, if metal shows various oxidation state, if metal shows the multiple oxidation state, I tell you how this question was asked. If it shows multiple oxidation state, then what happens? The halide with higher oxidation state is more covalent. Halide with higher oxidation state is more covalent. For example, we have PbCl4, correct? And PbCl2. This is covalent and this is ionic. They're going to get you trouble like this, no? You have SnCl4 and SnCl2. Then you have SbCl5, SbCl5 and SbCl3, antimony chloride. So this kind of question can be, and then we have also over here, next we'll continue. Highest oxidation state is in their fluoride. So highest oxidation state is achieved, yes, achieved in fluoride compound. In fluoride compound. Okay. So these are all the points that we have to take down. Take down this much and then we'll go to the next one. That is haloacids and their reactivity, stability and all that. When you finish, you tell me. Yeah? Finished?
I also checked.
Oh, sure. No, I'm also checking it's not hanging. I told you there's some software issue. The desktop is getting hanged. So I'm also checking actually whether if I'm moving. Okay, great. Now we come to what? Reaction with hydrogen. The next we are coming to is reaction with hydrogen. Reaction with hydrogen. So what happens? Decreasing order of reactivity. Decreasing order of reactivity. What do we realize? It is fluorine greater than chlorine, greater than bromine, greater than iodine. For example, if hydrogen and fluorine are just even mixed in dark, absolutely, still it reacts explosively. So hydrogen reacts with fluorine in dark to form 2HF, and that is explosive reaction. So you can imagine the reactivity of this in dark. Whereas they react in heat, sunlight. H2 plus Cl2 in diffuse sunlight. It forms 2HCl. H2 plus Br2, you have to heat it. So you get 2HBr. Then what do you have? H2 plus I2, you heat it. But it's a reversible reaction. So this is the indication of the first point that I'm saying. So this could be MCQ on its own. Is this clear? Now what happens is, now we are talking about the halo acids. Halo acid form. When you say a halo acid, we have HF, HCl, HBr, HI. Okay. When you say it's an acid, you say it's an acid when it dissociates very easily. So as the bond length of HI is more, it easily breaks, it can easily dissociate. So which will be the strongest here? See, acid strength is HF is a weak acid. Remember that. HF is a weak acid. Clear? Whereas HCl, HBr and HI are strong acids. See, understand this, but I know sometimes students think weak acid means it is not light, it is less reactive. It just simply dissociates incompletely. But among the corrosive nature, most corrosive is HF. Corrosive is a very different chemical property compared to acidity. Are you understanding? Compared to acidity. So HBr are strong acids. That means they dissociate completely. So you have HF greater than HF less than HF less than HCl less than HBr less than HF. So this would be a strong acid. But HF is most corrosive. HF is most corrosive. Is this point? That's a different property on its own, corrosive property. That has got nothing to do with its dissociation. As far as dissociation is concerned, HF is a weak acid. Is this clear? So then, of course, question is, then one more thing is, HF is a liquid. Okay, whereas HCl, HBr, HI, they are gases. Now you will immediately tell me, this is my experience in teaching so many years, sir, HCl in my college is in a water, it is a liquid. That's an aqueous solution of HF. Sorry, an aqueous solution of HCl is called hydrochloric acid. You've taken HCl gas and dissolved it. HF is a liquid, HCl, HBr. The normal HCl is probably it is a gas. Is this clear? Why is it a gas? So why is HF a liquid? Because it forms extensive hydrogen bonding. So they can ask which is a liquid, HF, HCl, HBr, HI. In a normal thing, what will people think of as the molecular weight increases? The physical state changes. They might write HI is a, what do you call? Liquid. HF is a liquid at room temperature. HCl, HBr, HI is gas. So what you are seeing is an aqueous solution of HCl, HBr, HI. Is this clear? Then thermal stability. HF is most stable, greater than HCl, greater than HBr, greater than HI. Why? Because HF bond is very strong. Small atomic size, so you have a very high bond energy. You have very high bond energy, and that is causing all the problem. Is this clear? Then, so take down this much, then we come to reducing property, very important. Yeah. So remember, HF is a weak acid, and then HF is a liquid. These are two very special properties of this halo acid. Okay, and that is what they ask. Then what do we have? We are reducing property. Remember, this was discussed in halogen derivative. That when we reacted directly with alkane, it formed HI with iodine. Alkane plus iodine formed alkyl iodide plus HI. But then we told you that this reaction is reversible because HI is a strong reducing agent. It reduces the halide back to the alkane and halogen. Is this point clear? So that is where there is a link to this. So when you talk of reducing property, so we have reducing property of halo. We are not talking about halogen. We are talking about halo acid. Halogens are oxidizing agents. Halo acid, HI is a strong reducing agent. So reducing property of halo acid. So what do we have? HI greater than HBr greater than HCl. We will not talk about HF because HF does not easily break down to form. Then we have next is uh, reactivity with oxygen. Reaction with oxygen. So we talk of reaction with oxygen of halogen. Fluorine reacts with oxygen to form OF2. Very special case. You know why? Because oxygen is less electronegative as compared to fluorine. But imagine if chlorine reacts with oxygen, what does it form? It forms Cl2O, Cl2O3, and Cl2O7. Chlorine heptachloride. This is clear. Chlorine heptaoxide. This is clear. Chlorine heptaoxide. Then bromine reacts with oxygen. And what does it form? They form Br2O and BrO2 and BrO3. So it may not form. Iodine reacts with oxygen to form what? It forms I2O4. It forms I2O5 and I2O7. It is clear. So these are the five. One thing is I2O5 is a strong oxidizing agent. Is a strong oxidizing agent and is used for detecting and is used for estimating and it is used for a very special statement they have made and it is used for estimating carbon monoxide. CO is carbon monoxide. Take down this much.
stop.
Okay. Now we come to two very important reactions from the entrance exam point of view. What are the two important? First is reaction with water. Looks very simple. Reaction with water. See, fluorine behaves very separately. All this we're going to talk again quickly with what are the anomalous behavior of fluorine. Okay, that's the next lecture. But then fluorine reacts with water. It forms HF plus O2. Whereas the other halogen, X2 is what? Cl2, Br2 and I2. They react with water to form HX plus HOX plus HX plus HOX. This is hypohalous acid. Hypohalous acid. That means what? HOCl, hypochlorous acid, hypobromous acid. Fluorine does not form hypohalous acid. So which does not form hypohalous acid? Fluorine, chlorine, bromine, iodine. That is the question we are aiming at. So what am I trying to tell you? Fluorine does not form. Fluorine does not form HOF, hypofluorous acid. You want me to write down that also? Hypofluorous acid. Fluorine does not form, whereas you have hypochlorous acid, hypobromous, and then stability of that we'll see again. This is clear. That is, hypochlorous will be less stable, hypoism. Then what happens is, next one is reaction with NaOH. We have two fantastic reactions where fluorine behaves differently. Reaction with NaOH. See, fluorine reacts with NaOH. Fluorine reacts with NaOH to form NaF plus H2 plus O2. So it forms ozonized oxygen. With NaOH, fluorine forms ozonized oxygen, mixture of oxygen and ozone. Whereas what happens with, say, NaOH, chlorine with cold NaOH. Cold. What will it form? It will form NaCl plus NaOCl, sodium hypochlorite, plus H2. So this will be a hypochlorite. Whereas chlorine with, say, hot NaOH. Then what will it form? It will form NaCl plus NaClO3. So this is sodium chlorate. So these three reactions with NaOH are very, very unique. Is this clear? Please take down. We'll stop here today. Okay. So I will be seeing you now on Sunday. Okay. Yeah, Sunday. Usual lecture, 5 to 6. So even for those who are on the live stream, the next lecture will be on Sunday, 5 o'clock to 6 o'clock. Sunday will be the 14th of February.